Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video we shall be discussing about electrical conduction through liquids and gases. So relax, do not go anywhere, I will be right back. You are welcome back to my school YouTube channel. Like I said earlier, in today's video we shall be discussing about electrical conduction through liquids and gases. So before we begin with our lesson, let's quickly run through the objective for today's video lesson. So objective number 1, explain the conditions under which liquids and gases conduct electricity. 2, explain the behavior of charges or charge carriers in liquids and gases in the electric field. And 3, describe an application each of electrical conduction through liquids and gases. So let's move to the next slide to begin with our lesson. So basically here we are going to be discussing about electrical conduction through liquid, and this is termed electrolysis. Okay, so we are going to be looking at the meaning of electrolysis. So electrolysis is the process of chemical decomposition of a liquid into its component parts due to the flow of electric current through it. Okay, so this is just the physics definition, but for chemistry both of them are the same. Okay, basically there's no much difference. So now let's discuss about some terms that are used in electrolysis, and the first one we are going to begin with electrolyte. Okay, so an electrolyte is a liquid or a molten substance which conducts electricity and is decomposed into its component parts in the process. Okay, so liquids that are good conductors of electricity are called electrolytes, while those that are poor conductors of electricity are called non-electrolytes. So some examples of electrolytes are solution of acid such as hydrochloric acid, then bases such as sodium hydroxide, and salts such as sodium chloride. Okay, so examples of non-electrolytes are organic compounds such as benzene, kerosene, etc. We have pure water, we also have sugar. Okay, they are all examples of non-electrolytes. Okay, now another term again that we will look at is electrodes. Okay, so electrodes are materials in the form of rods or plates through which current enters or leaves the electrolyte. Okay, and there are two types of electrodes. Okay, so we have the positive electrode, which is called the anode, and we also have the negative electrode, which is called the cathode. Okay, so the current enters the electrolyte through the anode and current leaves the electrolyte through the cathode. Okay, so let's move to the next slide. So on the next slide here, we're discussing about another term that's used in electrolysis, and that is voltmeter. Okay, so a voltmeter is the vessel containing the electrolyte and the electrodes, and it is a device for studying the flow of current through a liquid, and sometimes it is also referred to as an electrolytic cell. Okay, now let's talk about the Ionic theory and the motion of charged particles, ions, in electrolyte. Okay, so according to Ionic theory developed by a Swedish scientist called Arrhenius, an electrolyte dissociates into charged particles. So by dissociate means breaks down, okay, into charged particles called ions. Okay, and the process of dissociation is known as electrolytic dissociation. The dissociation occurs irrespective of whether or not an electric field is applied to the electrolyte, right? So in that case, the ions move randomly until a battery is connected to the electrodes in the voltmeter. So as soon as a potential difference is set up across the electrode, the positive ions drift, okay, or move to the cathode, that is the negative plate, while the negative ions drift or move to the anode, that is the positive plate. Okay, so this directional movement of ions is the electric current flowing through the electrolyte. The directional movement ceases as soon as the battery is disconnected and the ion move randomly again. Okay, so example is copper tetrasulfate 6 CuSO4, okay, solution, which dissociates into copper ions and tetrasulfate 6 ions. So this is just the chemical equation, okay, representing the electrolysis of copper tetrasulfate 6 solution. Okay, so the copper tetrasulfate 6 solution breaks down into copper ions and tetrasulfate 6 ions. Okay, so let's move to the next slide. Now, electrolytes are able to conduct electricity because in solution they dissociate into ions, whereas non-electrolytes in solution do not easily dissociate into ions. So for that reason, they don't conduct electricity. Okay, so the diagram you are seeing on the board is the diagram of a voltmeter. Okay, with the positive ions attracted to the negative rod or attracted to the cathode, and the negative ion attracted to the positive rod or the anode. Okay, so the positive ions attracted to the cathode are called cations, while the negative ions attracted to the anode are called anions. Okay, so let's see some examples of electrolysis. So example of electrolysis we are going to be looking at here, but then if you want more examples, then you can consult your chemistry textbook. Okay, so we are just going to be looking at one, and that is electrolysis of acidylated water. Okay, so acidylated water is just water that few drop of acid has been added. Okay, so here we need the Hoffman voltmeter, okay, and then the electrolyte, which is water, to which a few drops of H2SO4, that is tetrasulfate 6 acid, is added. Now let's move to the next slide. Now the electrodes are a pair of platinum plates at the bottom of two identical graduated tubes linked together by a funnel tube. Water dissociates into hydrogen ions and hydroxy ions. Okay, so hydrogen ion is H plus, while hydroxy ion is OH minus, that is hydroxy ion. Then tetrasulfate 6 acid dissociates into hydrogen ions and tetrasulfate 6 ions. So this is just the chemical equation, H2SO4, which represents the tetrasulfate 6 acid. Okay, dissociates or breaks down into hydrogen ions, okay, and tetrasulfate 6 ion. So when current is passed through, okay, so what happens? One, hydrogen ions drift to the cathode where they receive electrons to form neutral hydrogen atoms, and this combines in pair to form hydrogen molecule, while the hydroxy ions drift to the anode and are discharged more easily than the tetrasulfate 6 ion. Okay, and there are reasons for that. Okay, so you can also consult your chemistry textbook to see the reason for that, why the hydroxy ion is discharged in preference to the tetrasulfate 6 ion. Okay, at the anode, the hydroxy ions lose electrons, resulting in the formation of oxygen and water. So this is the chemical equation representing that reaction. So here we have 4 moles of hydroxy ion. So this dissociates into oxygen and water, then plus 4 electrons. So the oxygen formed collects at the upper part of the tube bearing the anode. Let's move to the next slide. Why the tetrasulfate 6 ions remains in solution. So the volume of hydrogen is twice the volume of oxygen collected. So this is the Hoffman voltmeter for the electrolysis of acidylated acid. Okay, so this represents the diagram. Okay, so let's move to the next slide. Now, on the next slide, we are going to be discussing about a scientist, okay, who discovered the 2 laws of electrolysis. And the name of this scientist is Faraday. So here we are going to be looking at Faraday's laws of electrolysis. So Faraday discovered 2 laws of electrolysis from the result of his experiment. So one of the law, which is the first one, states that the mass m of a substance liberated or deposited during the process of electrolysis is directly proportional to the quantity of current Q that has passed through the electrolyte. Okay, so what this simply means that the more current you pass through the electrolyte, then the more the mass of the substance deposited, okay, during the process of electrolysis. So mathematically, okay, what Faraday's first law of electrolysis is trying to tell us that the mass of the substance deposited during the process of electrolysis is directly proportional to the quantity of electricity that has passed through the electrolyte. Okay, but remember that Q is equals to IT, where I is current, and current is in amperes, and T is time, and time is measured in seconds, okay, during which the current flows. So mathematically, in place of Q, we can replace it with IT, since Q is equal to IT. So anywhere we see Q here, we can replace it with IT, so that we can as well say that M, which is the mass of substance deposited, is directly proportional to the current, okay, and the time during which the current flows. Okay, but of course, this is just a relationship, okay, showing the relationship between the mass of substance deposited and the quantity of electricity. Okay, so we can't actually do anything with this, so we have to introduce a constant, right? So that constant we are introducing is Z, so that M now becomes equals to ZIT. Okay, so if we decide to make the Z the subject of formula by simply dividing both sides by IT, we'll be having Z to be equals to M all over IT. Okay, thus the factors which affect mass of substance deposited are, let's move to the next slide so that we can see the factors, and one of them is current, time, then we have electrochemical equivalent, okay, often denoted with E.E.E, okay, and represented with letter Z. So that Z that we actually introduced into that relationship, M is directly proportional to Q, is called electrochemical equivalent. Okay, so the electrochemical equivalent of a substance is the mass of that substance deposited by 1 coulomb of electricity in a process of electrolysis, or we can as well still define it as the ratio of the mass of substance deposited in a process of electrolysis to the quantity of electricity that passed through the electrolyte. Okay, and each unit is grams per coulomb, which is G, then C raised to power minus 1, okay, meaning grams per coulomb, or you can as well write it G then slash C, they mean the same thing, grams per coulomb. Now let's deal with the second law. So the Faraday's second law of electrolysis states that the mass of different substances deposited during electrolysis, when the same quantity of current passed through different voltammeters in series, is directly proportional to the chemical equivalent of the substance. So mathematically, M1 all over M2 is equals to C1 all over C2. Okay, so M1 represents mass of one of the substance, while M2 represents the mass of the other substance, while C1 the electrochemical equivalent of one substance, then C2 the electrochemical equivalent of the other substance. Now let's discuss about the application, okay, or the uses of electrolysis. So let's begin with the first one, which is electroplating. Okay, and this is one of the industrial applications of electrolysis. Okay, so electroplating is the process of coating a metallic object with another metal to improve its appearance or to safeguard it against corrosion. So corrosion has to do with rusting. Okay, so generally, let's move to the next slide. Now this part is very, very important. So generally, the material to be electroplated is used as the cathode. This is very important. The material to be electroplated is used as the cathode, while the anode is made up of the material that is used in electroplating the other. The electrolyte is a solution of salt of the metal to be deposited. Now let's see, for an example, in silver plating of spoon, the spoon is made the cathode, while the anode is a pure silver rod, while the electrolyte is silver triisonitrate 5 solution. Okay, so another application of electrolysis is calibration of an ammeter. So basically the essence here is to determine any possible error in the calibration of an ammeter so as to know the correction to be applied to any reading recorded by the ammeter. This is obtained by an experiment based on Faraday's first law of electrolysis. Then we also have number 3, which is the purification of metals, and this is another example of industrial application of electrolysis. Okay, so for example, to purify copper, the impure copper is made the anode, while pure copper is made the cathode. So copper ions are dissolved from the anode and are deposited at the cathode, leaving impurities in the solution. Let's move to the next slide to see the last application, and that is preparation of metals from their compound. So if you want to know more about this, you can as well consult your chemistry textbook. Okay, now let's discuss about Faraday. Okay, so the term Faraday is the minimum quantity of electricity required to liberate 1 mole of ion of a univalent element. So when we say univalent element, we simply refer to those elements that have just only one electron on their atomos share, okay? And a good example is those elements found in the group 1, okay, of the periodic table. They are all examples of univalent element. So an ion of a univalent element has a single charge, while an ion of a divalent element has double charges, okay, has double charges, etc. So when we say divalent element, we are simply saying that these elements have 2 electrons on their atomos share, okay, and good examples are the group 2 elements on the periodic table, okay. So 1 Faraday is equals to 96,500 coulombs, okay, and this is equal to Faraday constant, okay. So just take note of that. 1 Faraday is equals to 96,500 coulombs. But remember that 1 Faraday is equals to 1 mole of univalent element. So in that case, 2 Faraday will be equals to 1 mole of divalent element. 1 mole of electrons contain Avogadro's number, okay, and this is also true for atom, and this is also true for molecules. So just take note of that. And that Faraday number is equals to 6.02 times 10 raised to power 23, okay, times 10 raised to power 23 of electrons, right? So the mass of substance deposited or liberated in a process of electrolysis is related to the relative atomic mass of the substance as follows. Mi all over Qi is equals to Mr all over QR. So what does Mi represent? So Mi represents the mass of substance deposited, while Mr represents the relative atomic mass of the substance. Let's move to the next slide. While Q1 represents quantity of electricity that passed through the electrolyte. But remember that Qi is equals to IT, right? While QR represents the quantity of electricity required to liberate 1 mole of electron. Now remember that we said earlier on that 1 Faraday equals to 1 mole of electron, right? And we know that 1 mole of electron contains the Avogadro number, okay, which is 6.02 times 10 raised to power 23 electron. So if 1 Faraday is equals to 1 mole of electron, then 1 Faraday is also equal to 6.02 times 10 raised to power 23 electrons. Therefore, if we decide to make an electron the subject of formula, therefore 1 electron E is equals to 1 Faraday divided by 6.02 times 10 raised to power 23. Therefore, 1 electronic charge E is equals to Faraday constant divided by Avogadro's number. That is, E is equals to 96,500 divided by 6.02 times 10 raised to power 23, and that is equals to 1.60 times 10 raised to power 19, okay? And that is why the value, okay, of 1 electronic charge is equals to 1.60 times 10 raised to power minus 19. So this is where this value is gotten from, okay? So this is where we draw the curtain for the preview of today's video. But you can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, you will learn about the application of cathode ray. You also learn about electrical conduction through gases. You also learn about the difference and similarities between thermonic emission and liquid vaporization, and many more. And don't forget, at the end of the lesson too, we also have some work example just to drive home what we have done in the video. So I believe you enjoyed the preview of the part you've just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we upload the next videos.